given that the potential energy, the 5.9 Newton centimeters, is the energy of the rail, well, we're going to convert this to more standard units. The standard unit of energy is the Newton meter. So that the centimeter being 100th of a meter, 5.9 Newton centimeters will be 100th of that number of Newton meters, or 0.059 Newton meters. And the Newton meter, as you should know from the introductory problems, is a joule. So we have 0.059 joules of potential energy. Now, we note that the rail mass is 0.2 kilograms. We can obtain that from a pan balance. We could deflect a pendulum by the weight of the rail mass. One way or another, we can determine this. What we did was we weighed the thing and found out that it weighs 2 newtons, and 2 newtons is just about 0.2 kilograms. So we say that the mass is 0.2 kilograms. Now, if the potential energy, the 5.9 Newton centimeters, 0.059 Newton meters, or 0.059 joules of potential energy that we stored in that rubber band, hypothetically, is all transferred into kinetic energy. Now, that's not really going to happen. If we did 0.059 joules of work, probably 10% of that's going to go into thermal energy. And there will be some other losses due to friction and other things. But if the potential energy, if all the potential energy becomes rail kinetic, how fast is the rail going to be moving? Okay, well, we know the mass of the rail, and kinetic energy we know is 1/2 mv squared. So we know that the rail kinetic energy is 1/2 mv squared. So that when 1/2 mv squared is 0.059 joules, we can easily solve to see that V is going to be the square root of 2 times 0.059 joules over the mass. And if the mass is 0.2 kilograms, this is going to give us a velocity. Now, we want to see just how the units on this calculation work out. So let's look at the calculation where we simplify this expression for the velocity. As we saw, the velocity was 2 times 0.059 joules over 0.2 kilograms. The numbers we can divide out very easily, but what in the world is a joule over a kilogram? Remember, we never do calculations without units. I will always penalize if you do calculations without units. So always remember to put units in all your calculations. The square root in any case separates into 2 square roots, a square root of 0.59 times the square root of the unit, joules per kilogram. What's a joule? Well, we saw a minute ago that a joule is a Newton meter. So we have 0.77 Newton meters per kilogram. Okay, well, we're doing all right. Notice that meters and kilograms are fundamental units. Meters, kilograms, seconds, and later on coulombs are going to be our 4 fundamental units in physics. It would be nice if we could express our newtons in fundamental units. That's fairly easy to do. How do we get a newton? A newton is the unit of force that accelerates 1 kilogram at 1 meter per second squared. Newtons are obtained from Newton's second law, where we multiply mass times acceleration, so that our newton becomes a unit of mass times acceleration, or kilograms times meters per second squared, just using the units of Newton's second law. We see that the kilograms will divide, give us 1, so we're done with those. A meter per second squared times a meter is a meter squared per second squared, so that we end up with 0.77 square root of meter squared per second squared, and the square root of that's just meters per second. So we see that the rail should be moving at 0.77 meters per second.